I talk about how to work music recognition. How to music recognition app. Many applications that allow us to recognize the song we like anywhere we entered our lives. So have you ever wondered how these apps work or what is happening in the background? Mobile technologies, along with the enormous progress in audio signal processing, have given algorithm developers the ability to create music recognizer. The basic working principle of these applications will create a fingerprint of the record audio file and ask it to the database. If there is an audio file with the same fingerprint in the database, it will give you the name of song you are listening to successful. Analog to digital sampling a signal. What is the sound really? Is it a kind of mystical material that we can't touch but flies into our ears and makes us hear something? Of course, that's not exactly the case. We know in reality that sound is a vibration uh, propagating as a mechanical pressure and displacement wave in a medium such as air or water. When this vibration comes to our ears, especially the eardrum, it moves to tiny bones that transmits the vibration to the tiny hair cells deep in our inner ear. Finally, small hair cells generate electrical impulses that are transmitted to our brain via the auditory ear nerve. Recorders imitate this process very closely, using the pressure of the sound wave to convert it into an electrical signal. The real sound wave in the air is a continuous pressure signal. In a microphone, the first electrical component to encounter this signal translates it into an analog voltage signal, again continuous. This continuous signal is not that useful in the digital world, so before it can be processed, it must be converted into separate signal that can be stored digitally. This is done by capturing a digital value representing at the amplitude of the signal. The conversions involves quantizing the input and necessarily brings a small amount of error. Thus, instead of a single conversion, an analog to digital converter performs many conversions on very small parts of the signal, a process known as sampling. This analog signal, this digital signal. Acoustic fingerprint. To take advantage of the voice fingerprint, you provide an audio file and get an output after a certain number of conversions. This output carries the fingerprint of that audio file. We're looking at the values of the fingerprints. It's completely opaque. This is a fingerprints contents. Comparison and hashing. This setup is music recognition's algorithms two main steps. All voice fingerprints algorithm go through two conversion steps. We want to protect as much relevant information as possible with the smallest fingerprints. Uh, Search time closely size plus data format. The first step we need to implement to compress the array is simple Huffman coding that allows the same amount of information to be represented in a more compact way. Uh, Now we are variable that keeps the same information much more accurate and less space. Uh, Hash type uh, equal to all hash type. At a higher level, voice fingerprint algorithms try to achieve a similar goal, converting an audio signal into the most compact and convenient format for storage and search. Voice fingerprints do not require lossless coding. There is no need to recreates the signal of fingerprints. The only condition is that fingerprints of the same value must come from the same or similar sound. Since we don't need reconstruct the initial data, we can perform a different final transformation step on the tuple. This code is useful. Voice fingerprints are similar. Some are equal because they come from some source, while others are due to a random hash collision. How to compress an audio signal? There are a wide variety of file formats, MPH, FLAC, and they all produce different byte representations. All fingerprints algorithm force decode the input file of a raw wave format. Sound fingerprinting is no exception. After decoding the audio file, we can focus on the following features of the audio file: number of channels, mono, stereo, or other; sample rate, typically 44.1 kHz; bit depth, typically 18.16 or 22 32 bits per sample. If we have a 1 minute audio file sampled at 44.1 kHz with 32 bits per sample, we need 21 million 1068 hundred and bytes to store. 2 multiply 60 multiply 44,100 multiply 32 divided 8. It means 20 megabyte of storage for only 1 minute of audio content. Record capture audio. It is easy to record a sampled audio signal. Since modern sound cards already come with analog to digital converters, it remains only to choose a programming language and find a suitable library. This is example Java code. Read the data target data line. In this example, the running flag is a global variable being stopped by another thread. For example, if we have the GUI with the stop button. Time domain and frequency domain. What wave and byte sequence are signal recorded in the time domain? Time history signal represents the change in amplitude of the signal over time. It is possible to represent any time domain signal by simply giving the set of frequency, amplitudes, and phases corresponding to each sinusoid that makes up the signal. This representation of the signal is known as the frequency domain. In some ways, the frequency domain acts as a kind of fingerprints or signature for the time domain signal, providing a static representation of a dynamic signal. This is time domain, this is frequency domain. Fingerprints a song. One unfortunate side effect of the FFT is that we lost too much information about timing. For a 3-minute song, we see all the frequency and size, but we have no idea when they appeared in the song. However, this is the key information that makes the song what it is. However, we need to know at what point each frequency originates. Therefore, we offer some kind of floating window or data stack and transform only that part of the information. The size of each piece can be determined in several different ways. This is this code. In the inner loop, we put the time history data into a complex number whose imaginary part is 0. In the outer loop, We enumerate all the parts and do an FFT analysis on each. Once we know about the frequency structure of the signal, we can start creating our digital fingerprint of the song. This is the most important parts of the entire Shazam voice recognition process. The main challenge is how to discussing which frequencies are most important in the ocean of the frequencies captured. In tutorial, we look frequencies of the highest magnitude. But the range of powerful frequencies in a song can range from low CC1 to high CC8. This is a huge range that needs to be addressed. Therefore, instead of analyzes the entire frequency range at once, we can select several small range selected based on common frequencies of the musical components and analyze each separately. For example, we can use range that this guy choose to implement the Shazam algorithm. These are 13 Hz to 40 Hz, 40 Hz to 80 Hz, and 80 Hz to 120 Hz for low tones, and 120 Hz to 180 Hz, and 180 Hz to 300 Hz for medium and higher tones. We can now simply determine the frequency of the highest magnitude in each range. This information creates a signature for this part of the song, which becomes part of fingerprints of the song a while. For easy voice search, this signature becomes the key to hash table. The corresponding value is the time this frequency sequence appears in the song along with the song ID. Here is an example of how these records might appear in the database. This part hashtag time sequence for audio files song and artist name. If we run a whole library of song through this music identification process, we can build up database with a complete fingerprints of every song in the library. Song identification. To identify a song currently playing at the club, we record the song with our phone and pass the recording throughout the same voice fingerprinting process as above. Then we can start searching the database for matching hashtags. As it happens, most hashtags will correspond of the music identifier of more than one song. For example, it could be that a track A is exactly like a track E, not E. Of course, this is not surprising. Musicians have always borrowed layers and riffs from each other, and these days the producers are exemplifying all of the other songs time. Every time we need a hashtag, the number of possible matches decreases, but it's likely this information alone will not reduce that match a single song. So there is one more thing we need to check with our music recognition algorithm, and that is timing. The sample we recorded at the club can be from any point in the song, so we cannot match the timestamp of the matching hash to timestamp of our sample. However, we'll multiply matching hashes. We need to analyze the relative timing of match and thus increase our precision. For example, if you look at the table above, you will see that hashtag 30, 51, 99, 121, 195 correspond to both song A and song E. If we match the hash a second later, 24, 57, 95, 111, 200. This would be another match for song A, but in this case we know that both the hash and time difference match. From top to bottom, how does Shazam work? To answer this question, here is a top-down overview of the entire music recognition and matching process. Initial song from the user, capturing to conversion data frequency domain, to fingerprinting, to storage the user. The database can be quite large for this type of system, so it is important to use some kind of scalable database. There is no special need for relations and the data model becomes quite simple, so it's a good case to use some kind of NoSQL database. Thank you for listening.